When installing a 150 amp, 120/240 volts load center 800 feet away from a meter main service using two 37.5 kilovolt amps isolation transformers to step up the voltage to 480 volts and then back down, you are indeed creating a separately derived system. This means that the grounding requirements differ from a standard service. The ground path from the main service to the load center is not required because the isolation transformers provide the necessary electrical isolation and establish a new grounding point at the load center. However, it's crucial to understand the role of the neutral conductor in this configuration. The neutral conductor is still required in a separately derived system. It is derived from the X0 zone lugs of the transformer on the step-down side, which is located at the load center. The neutral conductor provides a return path for unbalanced loads and prevents overvoltages on the circuit. It is essential for proper system operation and safety. Even though the isolation transformers step up and down the voltage, they still require a neutral conductor to establish the reference point for the system. For the installation, the following conductors are needed. Firstly, two conductors, phase A and phase B, from the main service to the isolation transformer on the step-up side at the meter location. Secondly, three conductors, phase A, phase B, and neutral, from the isolation transformer on the step-down side at the load center location to the load center. The ground path will be established through the transformer grounding system at both locations. Let's delve deeper into the function of the neutral conductor. The neutral conductor is a critical part of a three-wire, single-phase system, particularly when supplying 120/240 volts loads. It serves as the return path for current from 120-volt circuits. Without a neutral, the voltage on these circuits can become unstable, leading to equipment damage or malfunction. In a separately derived system, the transformer creates a new neutral point. This new neutral must be properly grounded to ensure safety and proper operation. The grounding electrode system at the transformer should comply with the National Electrical Code (NEC) requirements. This usually involves connecting the neutral to a grounding electrode such as a ground rod, metallic water pipe, or concrete encased electrode. The size of the grounding electrode conductor is determined by NEC Table 250.66. based on the size of the derived phase conductors. Let's consider some specific grounding requirements for separately derived systems, as outlined in the NEC. According to NEC section 250.30, the grounding electrode conductor must be connected to the neutral point of the separately derived system. This connection should be made at the same location where the system bonding jumper is connected. The system bonding jumper is a conductor that connects the neutral conductor to the equipment grounding conductor at the source of the separately derived system, which in this case is a step-down transformer. The size of the system bonding jumper is determined by NEC Table 250.102 based on the size of the derived phase conductors. The equipment grounding conductors must be installed with the circuit conductors to provide a low impedance path for fault current. This is essential for the operation of overcurrent protective devices such as circuit breakers and fuses. The equipment grounding conductors must be connected to all non-current carrying metal parts of equipment, such as enclosures, raceways, and motor frames. It's also important to understand the difference between a grounded conductor, which is the neutral, and a grounding conductor, which is used for safety grounding. The neutral carries current under normal operating conditions, while the grounding conductor only carries current during a fault. The two should never be connected except at the source of the separately derived system. Now let's discuss the implications of not having a neutral conductor in the system. Without a neutral conductor, unbalanced loads will cause voltage imbalances, potentially damaging equipment connected to the 120-volt circuits. For example, if one 120-volt circuit is heavily loaded while the other is lightly loaded, the voltage in the heavily loaded circuit will drop, while the voltage in the lightly loaded circuit will rise. This can cause overheating, premature failure, or even fire. Furthermore, the absence of a neutral conductor can prevent overcurrent protective devices from operating properly. In the event of a ground fault, the fault current may not be high enough to trip the circuit breaker or blow the fuse, increasing the risk of electrical shock or fire. In summary, while the ground path from the main service to the load center is not required in a separately derived system using isolation transformers, the neutral conductor is absolutely essential. It provides a return path for unbalanced loads, prevents overvoltages, and ensures the proper operation of overcurrent protective devices. Always follow the NEC guidelines for grounding and bonding separately derived systems to ensure a safe and reliable electrical installation. To ensure your installation meets code requirements and operates safely, consider these additional factors. Firstly, conductor sizing. Properly size the conductors for the 480 volts and 120/240 volts circuits based on the load calculations and the ampacity of the conductors as specified in NEC Table 310.16. Remember to account for voltage drop over the 800-foot distance. Secondly, overcurrent protection. Provide appropriate overcurrent protection at both the primary and secondary sides of the transformers. This includes circuit breakers or fuses sized according to the transformer's rated current and the conductor ampacity. Thirdly, disconnects. Install readily accessible disconnect switches at both the main service and the load center to allow for safe isolation of the electrical system during maintenance or emergencies. Fourthly, labeling. Clearly label all components of the separately derived system, including transformers, disconnects, and panel boards to indicate their function and voltage ratings. Fifthly, surge protection. Consider installing surge protective devices, SPDs, at both the main service and the load center to protect sensitive electronic equipment from voltage surges caused by lightning or other transient events. Sixthly, inspection. Have the completed installation inspected by a qualified electrical inspector to ensure compliance with all applicable codes and standards. Remember that working with electricity can be dangerous, and it is always best to consult with a licensed electrician if you are unsure about any aspect of the installation. A professional electrician will have the knowledge and experience to ensure that the system is installed safely and correctly. Let's explore the practical aspects of grounding and bonding in a separately derived system. The grounding electrode system at the step-down transformer location should be installed in accordance with NEC section 250.50. This section requires that all available grounding electrodes be bonded together to form a single grounding electrode system. Common grounding electrodes include ground rods, metallic water pipes, and concrete encased electrodes. If a ground rod is used, it must be at least 8 feet long and driven into the ground to a depth of at least 8 feet. If a metallic water pipe is used, it must be in direct contact with the earth for at least 10 feet. If a concrete encased electrode is used, it must be at least 20 feet long and encased in at least 2 inches of concrete. The grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the derived phase conductors. For example, if the derived phase conductors are 1/0 American wire gauge copper, the grounding electrode conductor must be at least number 6 American wire gauge copper. The system bonding jumper must be sized according to NEC Table 250.102, based on the size of the derived phase conductors. For example, if the derived phase conductors are 1/0 American wire gauge copper, the system bonding jumper must be at least number 6 American wire gauge copper. The equipment grounding conductors must be sized according to NEC Table 250.122, based on the size of the circuit conductors. For example, if the circuit conductors are number 12 American wire gauge copper, the equipment grounding conductor must be at least number 12 American wire gauge copper. It's also important to ensure that all connections are made properly and are tight. Loose connections can cause resistance, which can lead to overheating and even fire. Use appropriate connectors and tools for the job, and always follow the manufacturer's instructions. When working with transformers, it's important to understand their voltage and current ratings. The kilovolt amps rating of a transformer indicates its power handling capacity. In this case, the 237.5 kV amps transformers have a combined capacity of 75 kV amps, which should be sufficient for a 150 amps, 120/240 volts load center. However, it's important to verify that the transformer's voltage and current ratings are compatible with the supply voltage and the load requirements. The primary voltage of the transformer should match the supply voltage, which in this case is 480 volts. The secondary voltage of the transformer should match the load voltage, which in this case is 120/240 volts. The current rating of the transformer should be high enough to handle the load current. The current can be calculated by dividing the kilovolt amps rating by the voltage. For example, a 37.5 kilovolt amps transformer with a 480 volts primary has a primary current of 78.125 amps, which is calculated as 37,500 divided by 480. A 37.5 kilovolt amps transformer with a 120/240 volts secondary has a secondary current of 156.25 amps, which is calculated as 37,500 divided by 240. In addition to the grounding and bonding requirements, it's also important to consider the wiring methods used in the installation. The wiring methods must comply with the NEC and must be suitable for the environment in which they are installed. Common wiring methods include conduit, cable, and wire. Conduit is a rigid metal or plastic tubing that is used to protect wires from damage. Cable is a factory-assembled group of wires that are enclosed in a protective sheath. Wire is a single conductor that is used to carry current. The choice of wiring method depends on several factors, including the type of building, the location of the wiring, and the environmental conditions. For example, conduit is often used in commercial and industrial buildings because it provides excellent protection for the wires. Cable is often used in residential buildings because it is easier to install than conduit. Wire is often used in control circuits and low voltage applications. It's also important to ensure that the wiring is properly supported and secured. The NEC specifies the maximum spacing between supports for different types of wiring. For example, conduit must be supported every 10 feet, while cable must be supported every 4.5 feet. In addition to the technical aspects of the installation, it's also important to consider the safety aspects. Always work safely when working with electricity, and always follow the NEC guidelines. Wear appropriate personal protective equipment such as safety glasses, gloves, and a hard hat. Use insulated tools and equipment, and never work on live circuits. If you are unsure about any aspect of the installation, consult with a licensed electrician. A professional electrician will have the knowledge and experience to ensure that the system is installed safely and correctly. Remember, electrical safety is paramount.